I'm Dave Miller, Product Manager of the RS Product Group at PCB Load and Torque. Today, we will be looking at applying principles of torque, turn, and tension to the fastener testing process. If you have any questions as we proceed through the webinar here, please feel free to use the chat function in WebEx, or if you want, you can just simply wait until the end. We've allotted some time to take questions at the end of the webinar session here today. Now, previously on our webinar series, in part one, we reviewed the basics of fastener tightening technology. We took a look at the contributing factors to bolted joint integrity, the 5 basic things: clamp load, torque, angle, friction, and lubrication. We took a look at the 4 zones of tightening: rundown, alignment, elastic clamping, and yield. And we looked at the importance of friction in bolted joints. To kind of summarize part one, torque is the energy required to turn the fastener into the joint. Angle refers to the rotation of that fastener, how far it was turned. Clamp load is what holds the assembly together. Torque, needed to reach clamp load, is subject to variations in friction. And within the elastic clamping region, the angle of turn is proportional to our clamp load. Now, previously in part 2, we covered tightening strategies, the effects of assembly tooling on bolted joints, bolted joint audits, and torque angle signature analysis featuring the M-alpha method, which is very helpful for determining the amount of clamp load in a bolted joint. To summarize what we covered last week during part 2, we learned that to be effective, tightening strategies should be individualized for each specific application. The tool type and speed can have a great effect on assembly integrity. Critical bolted joints should be audited during or after assembly. And the M-alpha bolted joint auditing process can help determine our clamp load. So today, what we are going to cover will be the why and how of threaded fasteners. Why do we test fasteners, and how do we do it? We'll take a look at our fastener testing requirements. What's required to do it? We'll review some of the fastener standards, and we'll survey some of the more common test specifications. Obviously, there are dozens of test specifications for threaded fasteners, and a 20-minute webinar doesn't give us time to really do justice to more than a handful. So we'll take a look at the most important ones. Now, fasteners, as we've talked about in general terms, are used everywhere: in the automotive industry, in aerospace, in structural assembly, in the hardware business, miniature applications, oversized applications, many, many different industries. And all industries like this feature critical assemblies that need to be tightened properly. And what this means is that fasteners destined for critical assemblies need to perform during assembly and operation in a predictable fashion. So why do we test? Well, we want to verify the process repeatability of some of the important features of the fastener. How does the plating work? How is the coating working? Do the fasteners have the proper locking properties if they're designed to be a prevailing torque nut? we certainly want to be able to meet our customer performance expectations. And of course, there's always the acceptance testing for new business, where we're looking to get some new business and we need to be able to expand our testing capabilities to meet the requirements of that new business. And certainly we want to be able to verify the reliability of our assembled parts. Now this leads us to another question: how do we test? Lot and batch testing of fasteners prior to use requires specialized equipment. And what kind of equipment do we need? Well, first of all, we need equipment to apply and measure the torque energy transferred into the bolted joint. We need a load cell to measure clamp load and thread torque if needed. We need certified test parts as required by the test standards and specifications, test plate sets and fixtures to make the testing work. We need fixtures to secure the test parts during the testing. And we need some kind of software to record and process the acquired data and display, print, and plot our results. So what is required for the testing to be successful? We need to be able to take some direct measurements of the forces and loads and make some important calculations. We need to take measurements such as the input torque using some sort of rotary torque device. We need to be able to measure clamp load using a fastener tension load cell. We need to be able to measure thread torque, particularly if we're looking to calculate underhead and thread friction coefficients, using some sort of a torque tension load cell, sometimes called a research head. And we have to have some measurements of our fastener geometry, such as diameter, pitch, calculate pitch diameter, and so forth. We need to do some calculations for underhead torque, pitch torque, calculate a total or reference friction coefficient, calculate a thread friction coefficient, or the underhead friction coefficient. So what kind of equipment is required to do this? It may be a simple two-channel torque tension system capable of recording torque and angle, clamp load, capable of doing tool testing or performing joint analysis, and being able to provide numeric and graphic data to meet the customer requirements. It may be a portable measurement system used for fastener testing with or without a controlled drive motor. It could be used for assembly tool testing to verify the assembly of the process, or it can be used for bolted joint analysis and troubleshooting. Or our set of test equipment might be an automated fastener test system to do production lot and batch testing, to perform laboratory experimental testing on new processes, new plating or coating processes. Something that can provide us with a higher level of analysis, and something that can do friction coefficient testing, or do yield determination, or even do prevailing torque testing on lock nuts. The type of equipment will depend on what's required by the customer. Some customers may require numeric data only, such as this frictional report. Some customers may require graphing data in addition, something that can graphically display the amount of torque being applied to the fastener balanced with the amount of torque that's overcoming friction under the head or friction in the threads. So there are different tests for different types of fasteners. There's torque versus tension testing for coatings and plating, measures torque and clamp load, determines the torque at clamp or the amount of clamp load developed at a specific torque value, sometimes a K-factor calculation, the torque tension coefficient, is required. This is the most basic type of fastener testing that we'll find. There is also friction coefficient testing, where we'll measure torque, clamp, and thread torque, and then calculate friction coefficients, a reference or overall friction coefficient, and a K-factor, all at a specified torque or clamp value. We might need to do lock nut testing, prevailing on and off testing, measuring torque, angle, and clamp load, and determining breakthrough torque, our max first on torque, and let's say our minimum and maximum last off torque. We'll talk about that in a little bit in more detail. We might even need to do yield determination, where we measure torque and angle and clamp load and determine how much torque it took us to reach the yield point. What was our clamp load at that yield point? We may even go farther to determine the angle of ductility, which is the turn between clamp yield and the fastener failure point. Now, there are established test methods that are used in fastener testing. Fastener testing begins with testing standards that specify requirements so that test results for different processes of the same fastener can be reviewed and analyzed for friction testing. We can refer to standards such as DIN 946 and ISO 16047. Those are established standardized test methods often referred to in OEM or industry specifications. They contain some basic calculation methods. DIN 946 and ISO 16047 are doing basically the same thing. DIN was the original standard. ISO borrowed heavily from DIN and did rename some of the nomenclature. What you see here is an attempt to explain the differences between the two, but we're talking about the same basic things, and the calculation methods for the frictional coefficients are essentially the same. So let's take a look first at DIN 946. What is that all about? It provides standards for determining friction coefficients, specifies a tightening test for determining the coefficient of friction under specified conditions. It's applicable for comparison of assemblies with different finishes. It defines the basic parameters such as proof load, tightening torque, head friction torque, thread friction torque, and so forth. It provides formulas for calculating friction coefficients for threads, underhead, and reference friction. It defines the type of test equipment that's required. It outlines a test procedure. It specifies data requirements for the test report. And the process is fairly simple. It specifies an ambient temperature. It specifies a 30 RPM tightening speed. Although it does not specify target torque or clamp load where the torque value would be shut off, it does recommend, however, evaluations of the test data in terms of what was the thread friction coefficient, what was the head friction coefficient. And it provides guidelines for making comparisons based on that recorded and graphed data. So we might see a DIN 946 numeric report that looks something like this, where we see what our head, our thread friction, what our reference or total friction is, and some of the values that were recorded during the process. ISO 16047 has become widely accepted as the standard for friction coefficient testing worldwide. It's very similar to DIN 946 in that it specifies torque and clamp force testing to determine the tightening characteristics of threaded fasteners. It's applicable to bolts, screws, nuts made of carbon and alloy steels, not particularly applicable to threaded fasteners not under a tensile stress, thread-forming screws or self-locking fasteners. But for all other fasteners, threaded fasteners that are achieving some sort of clamp load, it's certainly applicable. The characteristics of the test may include torque coefficient K, total friction coefficient, thread friction coefficient, bearing surface friction coefficient, yield clamp, yield tightening, rotational angle, and of course the ultimate clamp force. These are all defined in the ISO standard. It also defines what sort of test equipment and test parts should be used, including plating and lubrication of those parts. It provides the formulas for calculating the various friction values and other evaluations, and it specifies the data requirements that should be included in a test report. So they're very similar, and perhaps ISO is the one that's most widely used worldwide at the present time. So what is the process with ISO 16047? Well, we want to make sure everything is at room temperature. We want to apply torque at a steady state, 10 to 40 RPM for small to medium fasteners, 5 to 15 RPM for fasteners over M16. We want to shut off our test, or at least measure, make our prime measurements at about 75% of our proof load. The recommended evaluations are very similar to the DIN standard. A torque coefficient, K factor, total friction, thread friction coefficients, yield clamp, yield tightening, ultimate values as well. So very similar to the DIN standard. Now an ISO test plot might look something like this, where we're going to graph our frictional values for our coefficients. So we can see our red line is our total friction, the blue line is the underhead friction coefficient, and the green line is the thread friction coefficient. We should be able to do this as part of the ISO standard based on our measurements. Now let's look at some of the other test specifications that are pretty common in use. In the automotive business, the SAE US Car 10 standard is pretty common. That defines the test method for determining the torque tension relationship of both external and internal metric threaded fasteners for measuring the frictional characteristics. It defines the assembly method, the single installation of the test sample nut with washer onto bolt, or bolt with washer into nut. It defines what the characteristics of the bolts or screws, the nuts and washers should be, plating, cleanliness, and so forth. And it also defines this and specifies the test equipment that should be used. Now the process for SAE US Car 10 is pretty common, pretty similar to what you might expect. It requires that you assemble the parts by hand, fully seat with a minimum of 2 threads protruding. Tells you that your shutoff should be 2% greater than the maximum torque at clamp load, typically 75% of our proof load. Our shutoff should be 1% greater than our clamp load. We should use 100 RPM. We should record our torque and tension. We should use new components for each test. And we should calculate the mean and 3 sigma limits for our torque at specified tension. And finally, we'll evaluate whether torque at tension meets the applied torque requirements of the individual finish specifications. So obviously the type of finish is going to determine what the standards are for our evaluation. Different plating and coating processes will produce different torque requirements. So part 1 of the US CAR 11 test report will look something like this, where we're looking at the frictional characteristics. So we can see our thread head, reference, K-factor, and so forth. The second part of the US CAR test report will look at the torque versus tension data. So here we can see at various tension values what the torque was achieved at those tension values for the 30 samples that we tested. Now let's take a look at GMW 3044. This is another fairly common test that's done. GMW 3044 covers the basic requirements for electroplated zinc on iron or steel, with provision for plating thickness, use or non-use of supplementary treatments, and corrosion resistance. It provides requirements for mechanical, physical corrosion resistance, and processing characteristics. It supplies processing requirements for post-treatment using lubricants, waxes, dipping solutions, etc., with codes applied to identify the different applications. And it identifies special surrogate bolt, nut, and washer part numbers. So we have to know what it is we're working with, what kind of fasteners we have, and we want to make sure we follow these specifications. Now the process for GMW 3044 is basic. Number 1, it's going to look at torque tension. And you'll notice here it references the SAE US CAR 11, as many OEM test specifications will do. They'll reference the ISO 16047 or DIN 946, or in this case, US CAR 11. In this case here, the testing will be done, except it wants a tightening speed of 30 RPM. Specifies a tension value of 28.3 kilonewtons, a torque of 37 newton meters plus or minus 5. Wants you to calculate 6 sigma values assigned for torque at specified tension, and the evaluation is based on specified torque tension specifications. Now for coefficient of friction, it identifies testing per DIN 946. The evaluation is based on specified friction coefficient specifications, and it identifies different codes for different types of lubrications. And based on those lubricants, the specifications for meeting the requirements of friction coefficients will vary. Another fairly common test specification is the JDM F15X1 for our friends at John Deere. The JDM standard specifies a neutral salt spray corrosion protection and torque clamp requirements for electroplated zinc with chromate. Very exciting stuff. Provides clamp force and torque values for metric fasteners from M3 up to M39, and for unified inch bolts, screws, or nuts, 1/4 inch up to 1.5 inches for defined by property or class. It defines the approved use of surrogate bolts for those who don't want to test or don't have the capability of testing an 1.5 inch bolt. Using a surrogate at 3/8 or 1/2 inch or M10 can be possible. and it defines a test bearing plate and test washers that need to be used for inch series as well as for metric fasteners. And the John Deere standards specifies a test method, identifies testing according to ISO 16047 with specifications provided for clearance hole and thickness of the test washer of inch series fasteners. Specified clamp force must be exceeded, and the evaluation will be based on torque at a specified clamp force. So you can see how they kind of mimic or mirror, I guess is the better word, mirror the test standards, and will often refer to DIN or ISO standards as required. There is the WZ102 standard. This one from our friends at Ford provides a test method for determining the torque and clamping force performance of fastener finishes specified in one of their standards and used on isometric threaded bolts, screws, studs, and nuts. It references ISO 16047 for defining the test method, test nuts, and use of surrogate bolts or production bolts or screws, and provides instructions for preparing test plates or washers. It defines the torque clamping force test in terms of RPM, 30 RPM plus or minus 3, which is pretty common. Specifies the coefficient of total friction is calculated, and the friction should be calculated at 75% of proof load. The bearing diameter should be determined per the print of the fastener, and the evaluation of friction for surrogate bolt friction values should be within specifications, as well as production bolt nominal values should fall within specified limits. So you're probably starting to see the commonality between the test specifications. There's some minor changes in terms of RPM. The test point, is it at 75% of proof load or 1% above 75% of proof load? But there's always some very similar things that you have to look for in the test specification when you're setting up and running a test. Now, for testing prevailing torque, we'll end up going to use a standard by the Industrial Fasteners Institute, IFI 100/107. So as an overview, IFI 100/107 establishes dimensional, mechanical, and performance requirements for 3 grades of prevailing torque steel hex nuts. Prevailing torque type lock nuts being frictionally resistant to rotation due to a self-contained prevailing torque feature, not a compressive load developed against the bearing surface of the nut. So in other words, what we're looking at is we're defining prevailing torque type nuts that are manufactured as being frictionally resistant to rotation. And that resistance to rotation is not due to the force on the bearing surface of the nut itself. It's on the threads. It provides guidelines and specifications for nut design, strength, grades, materials, processes, dimensions, and mechanical and performance requirements. It describes a method for determining proof load and describes test method for prevailing torque. The test process for IFI 100/107 specifies room temperature, a speed of 30 RPM. It recommends or advises that you advance the nut onto the bolt or the test mandrel until 3 to 5 threads are engaged. It then requests that you record the maximum torque during the tightening process, and that you continue tightening until the specified clamp load is reached. You back off the nut to no clamp, then measure torque for the next rotation, that next rotation after clamp load is removed, with the lowest value recorded as the minimum first removal torque. You continue on and back off until the locking device is disengaged. Typically, we'll call this the home position. Then we'll assemble the nut back to clamp load 2 more times. In some cases, we'll assemble the nut back onto the clamp load 4 more times. However, what we're looking at doing would be to record the minimum prevailing off torque on the final, the 3rd or 5th final removal. And we'll evaluate the data based on the listed specifications. So what we might see on our first run of an IFI test is something that looks like this, where we start on the right side and we increase our torque as we engage our prevailing torque feature in our lock nut. At some point, we begin to contact that lock nut, or contact that lock nut against the test washer, and our torque will increase as we continue to tighten the joint until we get to our upper clamp load value where the test is stopped. We then remove the nut, so we go in the counterclockwise direction, and we end up with this negative torque value that kind of mirrors what we had in the tightening process, and continue on until we return to the home position. What we will be looking for will be the prevailing on torque, the maximum prevailing on torque. Probably that's going to be around here on this particular test. On the off torque, we'll remove our clamp load. Once we get down to where we have no clamp load, then we'll look in this first rotation after clamp load is removed, and we'll look for our minimum torque value and our maximum torque value. So our minimum might be somewhere around here. This might be our maximum torque value. Then we loosen the fastener. After we do this for the first run, we'll repeat this for subsequent times, either 2 more times or 4 more times, and we'll get our final run that looks something like this, because what we're not doing is on our second through last runs, we're not taking it all the way up to clamp load. We're just taking it up to the verge of clamp load and then backing off. So again, what we're going to be looking for is in this first turn, after we have backed it off, we're going to be looking for our minimum and our maximum off. Now, the reason we're looking for this is to compare this to our original tightening process, with the idea that the 3rd or the 5th off is not going to degrade significantly from what the data showed for that first tightening. So our IFI lock nut test report is going to look something like this, where we can see what our maximum on torque value was the first time. We can see what our maximum off torque value was. And furthermore, what we'll be able to do is look at what these values were for our final off torque value and compare our max off and min off of the first removal to the max off and min off of the final removal. Note that many other OEM and international standards and specifications exist and may be required by customers depending on what their requirements are. So for fastener testing, what do you need to know before setting up and running a test? Well, you need to know what the specifications are for the proper test parts, the size, the plating, the state of lubrication, cleanliness. Do you have to clean them to remove all of the lubrication? Or just what are the requirements as specified by the test standard? You need to know what the temperature of your parts should be. Is it just ambient room temperature, or are there special specifications for this? You need to understand what your tool speed is. 30 RPM plus or minus 3, 10, 15, just what is the speed. We also need to understand what our shutoff point will be for torque, either by torque or by clamp load. We need to know the number of cycles that we're going to run the test. Is it just a single cycle friction test, or is it a multiple cycle prevailing torque lock nut test, or is it a multi-cycle test to look at durability of the fastener? We need to know what the assembly method is. Do we start at the very beginning threading the fastener on, or do we bring it up to the verge of clamp load? These will typically be identified in the test specification. And also the spec will identify the evaluation criteria, the torque at clamp load, the friction coefficient at a test point, the min-max on torque, min-max off torque, and so forth. And then the report format. What should be in the report format? This is always very important because you have to know what you have to display and provide to your customer. Do they want strictly numeric data, or do they need it in a graphic form, or both? And this is always pretty important when you're doing fastener testing. So what have we learned in all of three of these parts? I just kind of wanted to summarize that. So for those of you who were able to attend all three of these webinars, here's kind of a review of what we've covered. For those of you who were not able to catch all three of the webinars, you'll be receiving a link to the webinars, and you'll be able to go back and look at all three parts at your leisure. So we started out talking about the basics of torque, turn, and tension. We looked at the most important factors that contribute to joint integrity. We covered the 4 zones of fastener tightening. We looked at how torque, angle, and clamp load are measured. We determined how the state of friction, or we reviewed how the state of friction is determined. We looked at the role of friction and lubrication in successful bolted joint assemblies. And we looked at how friction coefficients are calculated and the 3 levels of determining the state of friction in the joint. Last week, we covered the tightening strategies, how the performance of assembly tools is verified, and we took a look at torque angle signature analysis and the importance of angle in helping determine proper clamp load. And today, we covered the whys and hows of different fastener types, evaluating them and testing them, and took a look at the standards that govern the testing processes, depending on just what you're looking at, what type of fastener you're looking at. I'd like to thank all the attendees who have taken time out of your busy afternoon. I hope that you found this series of webinars informative and helpful. I also want to thank Claire Odell and Emily Brannon at the Modal Shop for their awesome assistance. As mentioned, the link to this and the previous webinars will be sent to all attendees within the next few days. You'll be able to review sections at your own leisure. Please feel free to take advantage of that and share it with any of your associates as need be.